In this video, I'll be discussing Lewis dot symbols, which is basically a tool that allows us to keep track of valence electrons. So we know at this point that not all electrons in an atom are important, because when it comes down to chemical bondings, the valence electrons are the most important one. And therefore, we need to emphasize on the valence electrons. And by using the Lewis dot symbol, that is how we can keep track and only focus on the valence electron that an atom would have. So the Lewis dot symbol consists of the following. First, a chemical symbol. And the chemical symbol represents both the nucleus and all of the core or the inner electrons. And as for the valence electron, we put dots around the symbol, and they will then represent the amount of valence electron that an atom would have. And here are a few important points or key points that we need to remember about Lewis dot symbol. So Lewis dot symbol are based on the orbital diagram of an atom, but again, with emphasis on only the valence electron. And for second point, for nonmetal, for each unpaired orbital that we can see after we have drew the Lewis dot symbol, then each unpaired orbital would then be used by an atom to make a bond. So therefore, it's quite useful for us to be able to draw the Lewis dot symbol correctly, because we can use the Lewis dot symbol to now predict how many bonds that an atom would make. In this case, this refers to only the nonmetal. And many nonmetal undergo something that we call excitation or hybridization to maximize bonding. And here in this class right here, we will not focus so much on this excitation and hybridization, but in general chemistry, we'll spend more time in this. But in this case right here, we'll just point this out that many atoms, especially the nonmetal, undergo excitation or hybridization to maximize bonding. And we'll go over an example of this in a little bit. So now, let's learn how to write the Lewis dot symbol. So here are the several examples right here of breaking down to the group and some of the elements. So for an example, with potassium, the electron configuration of potassium is that it has the argon core followed by 4s1. And as for its orbital diagram, in the 4s, there's one electron. So there it is. How do we now write the Lewis dot symbol for this? Then to get started, first we put K, and this K right here, this symbol would represent both the nucleus and all of the core electron. And in this case, potassium have one valence electron, so therefore we put one dot surrounding it. And there it is. That is Lewis dot symbol with the one dot. And now we now have one valence electron. In chemical bonding, we see that potassium actually form one bond. And now moving on to another example, an element from group 2, in this case calcium. So the electron configuration in the orbital diagram of calcium would be argon 4s2. So in the 4s, there are two electrons in the opposite spin. Please note that the two electrons locate in the same orbital. So therefore, when we write the Lewis dot symbol, we have to make sure we put these two electrons right here together as a pair. So there you go, we put them together as a pair. And that's what the Lewis dot symbol of calcium would look like. Now, some textbooks make the mistake of putting the electron on different orbital by putting them on the two opposite sides of the calcium. And this is actually not correct. We have to put them together to show that they belong to the same orbital. So there it is. So this is incorrect if you ever to run into one. And now as for the amount of valence electron, calcium has two valence electrons. And in chemical bonding, it actually forms two bonds. Moving on to group 13. So please make that correction. This is group 13, boron. And the electron configuration of boron is that helium 2s2 and 2p1. So in this case right here, it has three valence electrons. Now, when we draw the orbital diagram of helium, of boron, this is what it would be. The 2s has 2 electrons in it. And now in the one of the p orbital, there's 1 electron in it. So initially, that's what it is. But if we were to be writing the little dot symbol of boron the way it is, it will be written as follows. Boron, and now we'll be having a pair of electrons. And this pair of electrons right here represent the 2 electrons they're in this orbital. And now there is another electron in here by itself on a separate orbital. And so therefore we're going to put another one right here. So that's what it will be. So basically here is kind of how it would go. We would imagine there are 4 spaces surrounding this, representing the 4 valence orbital. And again, all of the non-metal, a lot of them have 4 orbitals in them. So this is why that each of this space right here is a imaginary orbital. And now we're going to put the electron in. So in this case, then there are 2 electrons in the same orbital. So we put them in here. And another electron on a different orbital. So we put that over here. And now taking this imaginary orbital away, we would then have that. And that would then be its Lewis dot symbol. And in this case, it has 3 valence electrons. Now, if we go back to what we mentioned earlier before, that for each unpaired orbital, the atom can use it to make a bond. So based on the Lewis dot symbol of boron, both its Lewis dot symbol and all its orbital diagram, there's 1 orbital that has the unpaired electron in it. So technically speaking, boron will be able to make 1 bond. But then that is not what we observe right here. What we observe is that boron, just like many of the other non-metal, undergoes something that we call excitation or hybridization. Now, excitation and hybridization is the following. It is a mathematical combination of all of this orbital right here to produce 4 hybrids orbital. So basically, we take in the s orbital and the p orbital and combine them together. And in the end, we are now producing 4 hybrid orbital. If we start with 4 orbital before, we'll be producing 4 orbital in the end. And the key thing in here important to remember is the following. Earlier, before this hybridization, the energy gap between the 2s and the 2p, there's a gap between them in which that the 2p is higher in energy compared to the 2s. So this is why that we have to fill the electron in the 2s first before we fill them in the 2p. But after excitation and hybridization, we're now producing this 4 hybrids orbital, and all of them now have same energy on them. And because they have similar energy, therefore electron will then go and occupy each of this orbital right here singly first. And now, in this case, there are 4 orbital, and 3 of them have 1 electron on them. So therefore, after excitation, the Lewis dot symbol of boron will become the following. Now, the amount of electron it has is still 3, but in this case right here, it can make 3 bonds. So that is one thing very important that we need to realize about this hybridization or excitation. So it turned out that the more bond that an atom can make, the more stable it would be. And that is the driving force for why boron, just like most of the other non-metal that we see down below, actually undergo hybridization, because it can go from making 1 bond or less bond into now making up to 3 bonds or more bonds for the different types of element. And that is again the driving force of this hybridization. And we observe that for boron, it does not stay in this types of electron configuration or orbital diagram, but then this is how it exists in. So that way it can maximize bonding. And I'll move on to some other example. So again, for carbon, nitrogen, oxygen, chlorine, and many of these other non-metal right here, it is a fact that they actually undergo hybridization before they actually form chemical bond. So that way they can maximize bonding. So given the resultant orbitals after hybridization have taken place already, Let's now draw the Lewis dot symbol for this following element. So in the case of carbon now have 4 electrons in 4 different orbitals. So it would then have 4 dots around it. And now have 4 valence electrons. So the amount of valence electrons do not change in hybridization. But all it changes will be where the electrons locate in the different orbitals. And in this case right here, carbon have 4 unpaired orbitals in here. And it can use each of this unpaired orbital right here to make a bond. So therefore, carbon would then have 4 bonds. And now moving on to another example, nitrogens. So after hybridization, this will be the orbital diagrams of nitrogen right here. And based on it, Lewis dot symbol will be as follows. So you have 1 pair of electrons in here, and 3 of the other orbitals are unpaired. So here in this case right here, we will then see that nitrogen has 5 valence electrons, but because it has 3 unpaired orbitals, therefore it will be able to make 3 bonds. And similarly for oxygens, after hybridization, this is how its orbital diagram would look like. So in this case right here, the Lewis dot symbol of oxygen would then be oxygen. Now it has 2 pairs of electrons. So we put them here. We can put them anywhere, but then to make them symmetrical, we try to put the similar 2 pairs on the opposite side of each other. And we have 2 lone pairs right here. So therefore, there's 2 separate dots. And in this case, oxygen has 6 valence electrons, and it has 2 unpaired orbitals. So therefore, it can then make 2 bonds. And as for group 17, using the chlorine as an example, this is what its orbital diagram would look like. And now its Lewis dot symbol would then be as follows. So you have 3 pairs and 1 lone pair. It has 7 valence electrons, and now it can make 1 bond. And as for group 18, in this case right here, all of the orbitals are filled. So therefore, neon now have 8 valence electrons. And because it don't have any unpaired orbital, so therefore it makes 0 bond. So this is an example of the number of bonds that is very important that we recognize from the periodic table. So again, let's go over this again. Group 1, make 1 bond. Group 2, make 2 bonds. Now the types of bond that we see in here would then be mostly in the ionic bond. And as for group 13 make 3 bonds. So this is what it would be. So make 3 bonds. Group 14 make 4 bonds. Group 15 now make 3 bonds again. And group 16 make 2 bonds. Group 17 make 1 bond. And group 18 make 0 bond. So this is a very important trend that we need students to be able to recognize. That elements from different groups can make different number of bonds. And the explanation why that they can make those number of bonds can be explained by using the Lewis dot symbol or the orbital diagram.